Now we're going to do a class on ecology. And this is like very fundamental stuff to becoming a permaculture designer, basically. And I think understanding ecology will hopefully like open a lot of kind of doors, especially like perception wise for people, just getting a basic understanding of like how it is that, and like I said, this is very much a crash course. You can do a whole, you can study ecology for 6 years in university if you want, but hopefully I'll get through what I think are like some of the main points to understand about it. Okay, what is ecology firstly? It's the study of living and non-living things and their physical environment, right? That's it basically. Another way of putting it would be it's the study of ecosystems, right? And then we say, well, what's an ecosystem? An ecosystem is a community of biotic and abiotic, or living and non-living elements and their physical environment. And the set of relationships produces a series of patterns, really produces life, right? So what do I mean by that? Well, you can take any healthy ecosystem and you can sort of look at it through that lens, right? So if you take, say, an old growth forest, you have what are the living elements you have in the old growth forest? You have trees, you have grasses, you have shrubs, you have mycelium, you have fungi. What else do you have living in a forest?
Animals.
All the animals, all the birds, all the insects. All these things are existing in relationship to one another, and those relationships are producing basically more of the same thing, more life, right? And the non-living things are sunlight, water, wind, rocks, and therefore minerals in the soil. Minerals in the soil are just, when people talk about that, they're really just talking about tiny little bits of rocks. So that's it, right? It's those relationships that ecologists study, yeah. And then at this point, it's kind of like helpful to talk about the whole on thing we talked about yesterday, right? Because planet Earth, the term Gaia, the Gaia system, which is planet Earth, is one giant ecosystem, right? And you know, Gaia theory, described by James Lovelock in his book Gaia's Revenge, which he was talking about like climate change and that, you know, and he was one of the first people to proposit the theory that like planet Earth itself is one large, intelligent, living system, and there's a lot to that idea. But then within that, and it's again where the whole-on concept is interesting. Within that, there's an infinite number of little ecosystems that can be viewed on their own. And of course, they don't really make sense unless you know, they can only exist in relationship to the wider ecosystem as a whole, which is planet Earth, which only exists in you know, within the solar system, which only exists within the galaxy, blah, 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 right? But you know, but it is very useful to kind of break things up, right? And to be able to go like, okay, well, what are some common impressive ecosystems? And the reason we want to do that and study these things is because, remember our definition for permaculture yesterday, it's ecosystem design. That's what we're trying to do. We're trying to design farms, landscapes, communities, and we're trying to like get them to work like healthy ecosystems. So, well, what is it that healthy ecosystems do? First and foremost, they support and create life, right? And that's really the thing, you know, that's so amazing about them. So, you know, like what are some common ecosystems that we talk about? We've got forests, we've got grasslands, savannas, lakes and bodies of water, ponds, estuaries and wetlands would be, we mentioned that yesterday. Remember we said we were talking about mangroves yesterday. That mangroves are an extraordinary ecosystem because they've got that edge thing going on, but it's like they're the series of relationships that make up the ecosystem would be, you've got salt water, fresh water, lots of sunlight, lots of runoff from the mountains up above, huge bird population, huge fish and turtle population, and that all that interaction, all the relationships between those different things creates more. And this is the thing, it's like those sets of relationships create more mangroves, and then those mangroves create more life, and the thing goes on, and we call that upward spirals, right? So because we're going to talk about, so there's like certain things you can say, okay, so ecosystems, healthy ecosystems, and we know they're healthy because they've been around for a long time, and they keep doing their thing, and they keep existing, and they keep producing more life. So that kind of tells us that it's like, okay, they're doing something right. So they support and create a lot of life. They tend not to produce any waste. We talked about that yesterday. Part of what makes them healthy is the output of one thing is the input of something else. So what that really means in practice is there's a lot of beneficial interactions going on, right? Very active decay cycles. We always see this in healthy ecosystems. Something dies and it gets used really quickly, right? In a not healthy ecosystem, that doesn't happen. So, a barrio in Guatemala City is an ecosystem. There's living things, there's people, there's animals, mostly dogs. There's sunlight, there's water, and a lot of life is being supported, but the conditions for new life to thrive are not being met, right? So that's one thing. There's an awful lot of waste in a city or an urban environment. There's an awful lot of new inputs coming in and then not getting used and becoming a problem somewhere else, right? So the sewage is not being used in the place it's being generated. So that's a big difference from what happens in a forest, right? Like in a forest, the deer shits and the poop mixes with the leaves, and then the worms eat it and it grows to create more soil, right? Someone poops in a city and in a good case, it gets sent out through a complex system of piping and sent off somewhere else and maybe used there, and that's like best case scenario. A lot of cases in Guatemala City, for example, it would just fucking run straight down into the river, right? Out of the ecosystem, not get used, and then create a problem somewhere else. And it's the not using it is the problem, right? Like poop is not inherently bad. Unused poop is bad, right? Because then it accumulates and it overloads the capacity of the system to deal with it. And healthy ecosystems, really what they're doing is they're storing energy in large amounts. And that's what we're going to talk about now, right? Is this kind of basic, like, what is it? How is it that healthy ecosystems are able, and planet Earth in general is able to create the conditions for life to emerge and is able to support such a large amount of life? Well, firstly, really, and primarily, it's just large-scale energy capture, right? That's what it is. We talked about that yesterday. Remember we said, like, energy turns into matter, and then matter eventually, at some point, really far on in the life of the universe, turns into life, right? And so how does that happen? Well, it happens through plants. So in what you have in all ecosystems is you have producers, right? Producers are plants. They're the ones that harvest the primary energetic input on the planet through photosynthesis, right? And do people know what photosynthesis is? Yeah, it's sunlight plus carbon dioxide equals yeah, oxygen plus glucose. Plants' bodies are basically made of just long chains of carbon and sugar, really. It's just sugars rearranged in different forms. That's what they're made up of. And yeah, I mean, there's a bit more to it than that. The more complex the structure of the plant, the more minerals will be involved and all the rest of it. But the basic mechanism is just converting sunlight and carbon dioxide and water and transforming it into biomass, right? And so that biomass, you want to start seeing that if you're becoming an ecologist or a permaculturist, you want to start seeing that really in energetic terms, right? And producers or plants, they make that energy available to other life forms, right? So the next thing you get in the system in all ecosystems is you get decomposers. Right? So the decomposers are the little critters, the fungi, the microorganisms, the tiny little things that kind of exist in symbiosis to the roots of the plants usually, and to what's happening on the surface of the soil, because what plants do is they sort of shed their excess biomass and they drop it on the floor. And through their roots, they'll typically secrete out sugars and biomass that they're harvesting, and they'll make it available to what we call primary decomposers, right? So the primary decomposers are the fungi and the microorganisms, and then the secondary decomposers are the little anthropods and things like that, shredders, and then eventually you get like earthworms, right? And so this relationship between plants and primary, secondary, and tertiary decomposers builds soil, and it creates the possibility, as soil gets built, more plants can live, and the more soil there is, the bigger the plants can grow. And this is what we call like an upward spiral, right? Plants build soil allow plants to grow bigger and more complex, and the bigger the plants get, the more the primary decomposers have to consume and eat. And then eventually you get consumers, right? And the consumers are animals, basically, things that will like eat the leaves or eat the bugs or the insects, right? And again, in healthy ecosystems, that loop sort of stays closed, right? So what I mean by that is there's no energetic loss with that, right? So eventually as this cycle goes on, what's really happening energetically is the net energy in the system is increased, right? Because the capacity for photosynthesis is increased, right? And so there's one term, and it's the notion of entropy and syntropy, right? So we're just going to diverge really quickly and talk about this. Oh, here it is. So, entropy, do people know what that is?
Disorder, is it?
Yeah, yeah. Entropy is the amount of disorder in a system, right? And the second law of thermodynamics says that it has to increase over time, right? And you see this all the time. It's like you can't put the toothpaste back in the tube, right? If you make a sandcastle on the beach, that's like an ordered arrangement, and over time the wind and the rain will kind of like deplete it back out, and it will go back out into a non-ordered or kind of chaotic arrangement, right? And we know that that's true, and we know that it's there, and I think people are like very aware of it. And I was always fascinated by this. I remember when I was 12 or 13 in science class, I was like, but sir, like, what about evolution? Isn't that going in the opposite direction to entropy? And the teacher was like, well, actually, if you look at the solar system as a whole, the amount of disorder in the solar system is still increasing, was what he said to me. And I was like, what? And he was like, well, think about it. You've got a sun that's a highly ordered kind of system, and the energy from the sun is like streaming out through the universe, and only a little bit of it is getting captured on planet Earth. And so the overall disorder in the solar system is still increasing, and eventually the sun is going to explode, and so the law holds up. And I was like, okay. But I didn't realize, and he was right, that's true. But it missed the beautiful point, which is like, with a bit of that energy, making it go in the other direction is how you get all the life on this planet. Does that make sense? So you have a sun. The sun actually is just a sun is just a giant fusion reactor made out of helium atoms, basically, and it's highly ordered. And that energy is being emitted into our solar system. And a sun is a holon, and a solar system is a holon, and a galaxy, which is this whole system of solar systems, is another holon, right? But the solar system on its own, right? There's an energetic pulse to that, and most of the energy is going from the sun, where it's ordered, out into the universe, where it just disperses out basically into nothing, right? But a tiny amount of it, really tiny amount of it, is getting captured by plants. And that is actually that's the start of what we call syntropy, right? Because syntropy is the opposite to entropy. It's the ordering of things, right? And so, well, you think about it, the plants start to do this. They start to store the energy up. They combine the sunlight with basically water and carbon dioxide to make their bodies, and then they make that energy available to other living things through the process I just described, right? And so, kind of like, think of, when you see a forest, remember that used to just be bare rock, and there was no energetic capture going on. And then over time, basically through this process that I'm describing, you get through this kind of like upward spiral, right? Of a little bit of energy gets captured, and that energy that gets captured turns into, eventually through its life and death cycle, it turns into more fertile soil, which means more plants can grow, which means more energy can get captured, which means more soil gets created, which means more plants can grow. And this is the exact opposite to entropy, right? And we as human beings are like way out on the end of this process, right? you know, and that's why I think it's very important that we become conscious of the basic process and co-creators in it, because that's what humans can do on a good day, right? And I think when we're out of sync with it, that's when we really like start to suffer, right? So that's entropy and syntropy, and it's really what we're trying to do all the time as permaculturists is we're trying to increase the amount of energy that's stored kind of on our land. Yeah. And, you know, like that's a lot of what you do then as a permaculture designer, is you just sort of follow that, right? So, okay, what else can we say about ecosystems before I move on? There's this idea, it's kind of following on from the entropy syntropy thing. It's the source to sink idea. The idea that in every ecosystem there's a source of energy and a sink, right? And the sink is when the energy is no longer available. And really one of the things that defines healthy ecosystems is that there's a long time between the input and the sink, right? So if you talk about the sort of healthy old growth forest I mentioned, it's like, okay, so your sources of energy are rainwater, sun, carbon dioxide. Those are your basic inputs, right? Those come in, they get captured in not just the trees, but the shrubs and the bushes and the vines and all the different things that are growing all over the place. And they get held. And then they get made available to the primary, the secondary, the tertiary decomposers, and to, you know, eventually to the herbivores. Evolutionarily speaking, they come along kind of next, the herbivores, and they eat it and they poop it out, and that builds soil. And, you know, then an antelope gets eaten by a lion and the carcass decomposes eventually, but it's all about how many things it gets used by before it becomes unavailable. Because when it becomes unavailable, that's when it's sunk in. And a kind of a good way of understanding this is to think about oil, right? Everyone hates oil if you're environmentalist, but like, think about what is oil. It's the sink. It's dead dinosaurs and old forests, right? That has eventually sunk in, right? And now think about our role and what we're doing. It took me a long time to understand this, actually. Because, so everything that's alive is doing the same thing. Everything that's alive is challenging entropy, right? And so think about, you know, a mountainside here, right? And you get rain, that's an input, the source is the cloud, right? And the rain starts flowing down here. Now, the healthier the ecosystem, the longer the rain will get stored on the mountain, right? And it'll primarily get stored biologically through trees and grasses. And then animals. You know, bodies are made of water and sunlight essentially as well, energetically, if you look at it in those terms, right? Now, but eventually, just like in the sort of thing with the solar system I described, eventually entropy is going to win. Eventually this energy will like end up like in the bottom of the sea or the lake or whatever, right? It'll eventually kind of like run off here and it'll end up down at the bottom in a non-usable thing. Now think about, do you ever see what salmon do? Yes, they swim upstream. It's a really interesting thing to look at, right? Because really the salmon the salmon it's made up of all the stuff up here that washes down in here, and salmons are made up of minerals and organic matter and all the stuff that's kind of collected up here, washes down here. And they swim upriver against the current, and they go back to where they were born, and they lay their eggs, and then they die. And then that creates an extraordinary, in the place where they swim to, a huge feeding frenzy, right? Like bears and eagles and all these kinds of things descend on this place. It's an extraordinary thing to see. And then, you know, they die, and even botanists will study the DNA in the trees, and they'll find that, like, you get salmon DNA kind of in the trees that live on the edge of the places where this happens, right? And it's kind of an extraordinary thing to see. And I think the reason it's so extraordinary is actually then you realize, well, that's happening everywhere, right? So, you know, think about this again, the water flowing downhill. It's like it wants to flow down, but when you get grasses and trees that grow along the edge of the river, that's an upflow. The water's flowing down, but there's a bit of an upflow, right? And I'll take you guys when you do the waterfall hike, really, really look out for this, like this thing that happens where you get water flowing downhill, but when it flows down, it hits something, and there's enough of a shallowing out, what you'll get is it will start to form eddies, because the kinetic energy will turn into thermal energy. So the pace that the water picks up going downhill will give it enough energy to actually move back uphill. And this happens everywhere there's flowing water. This happens, and again, it's that same thing that we get with the sun. Most of it will go downhill, but a bit of it will spiral and go back uphill. And when it does that, it'll create a little ledge here, and then some trees or plants will grow along the edge of the river, and that's also the water is going uphill, right? So it's about how much up can you get in the down. That's what life is, right? And so, well, remember the oil? The oil is the same thing. The oil is down there, it's underground, it's ancient dead dinosaurs. And kind of interestingly, very interestingly, I think, it like wanted to come up out of the ground. And human beings came along, and we started helping with that. And everyone is like, oh, it's terrible, the oil, we shouldn't be doing it, it's awful. But I started to rethink about that, and I started to think, well, maybe actually that's one of our ecological functions, is to take all that energy and to move it back uphill and make it available again. No, we're not being very smart about how we're doing it. But if you think about it in those terms, it seems entirely plausible to me that if this is a huge reservoir of oil, of like now sunk, unavailable energy that used to be all this living stuff, and it is pure energy, and that's why when we turned it into people, that's what we did. Like, that's why we had so much population growth over the last kind of couple of 100 years, because we discovered this like massively abundant energy source, and you know, we went a bit crazy, right? And now where is it, all that oil? It's like it's up in the atmosphere as carbon dioxide, and it's floating around as plastic, most of it. And you know, a lot of people are like, whoa, that's fucking terrible, and maybe it is, I don't know, but it's like, we already know what's carbon dioxide. Yeah, which is a primary ingredient for trees. And are we going to run out of sunlight anytime soon? No. So it's like, if people would stop fucking bitching about it and just plant more trees, it would be like a lot more useful. It's not, I don't think, that bad. And it's like, yeah, all the plastic and stuff, when you see it, it's like, oh God, that's not great. But like, it's still just energy, and it's still usable. We haven't nature hasn't figured out how to use it yet, but it will, right? And like those big plastic islands they talk about, you know, you've heard about that, right? Like the plastic goes into the ocean and thermal currents, like or currents in the water, like cause it to accumulate together, and it starts to float, and it's a big ball of plastic basically, and it's like, oh god. But even that, it's like, whoa, it's accumulating again, and something will figure out how to break it down and make it usable, right? It like it's only a problem when it's not usable. Once it becomes usable and once it gets taken back up into the biosphere again, it's fine. And nature is always finding ways of doing that anyway. So over 10,000 years, I wouldn't be that worried. Like, especially if we start to like kind of correct it now. And like, so obviously like with plastic, well, what do you want to do? You don't want to burn it. You want to try and like break it down or turn it into like probably a building material or something like that. But it's like, it's just, we've actually just increased the available energy in the system by mining the oil, right? So anyway, that's a big kind of aside. Okay, so we'll try and like land this now in some like usable information or usable sort of like practical steps, because we're trying to design ecosystems, remember, right? So, well, there's one thing to remember, right? I sort of described it already. There's this really important process in ecology called succession. And succession is the process from disturbance to stability in ecology, right? So disturbance is like, there was a fire, there was a landslide, or there was just like man-made desertification is a disturbance. You know, like man-made desertification is like removing the trees and grasses and growing soy or corn for like 20 years in a row, right? Look at that system in terms of like the what I just described, right? Like there's no energy capture, or there's nowhere near enough energy capture in a monoculture of soy, right? Because it's an annual grain. It lives, it dies, and unlike a tree, it doesn't like stay there and continually produce leaf litter and feed the things around it. It just lives, it dies, they remove all the byproducts, and so the soil gradually like decreases in fertility, and that's why you need chemical fertilizers, right? Because you need an energetic input, because you've taken your photosynthesizers out of the system, right? And so 20 years or 30 years of doing that represents a huge ecological disturbance. So it's like, and our generation now are going to really be confronted with like, what are we going to do with all this farmland that we've like fucked up, and what are we going to do with all these urban areas that we haven't really managed properly? And succession kind of holds the key, I think, in my opinion, right? Because so what happens in a succession? In succession, so you get this like bare, desertified piece of land. Tony, you get this bare, desertified piece of land. This is a problem now because the sun hits it and it just like cracks it. It dries it out. There's nothing to capture the sun's energy. Water falls on it, and instead of soaking in, if the thing is bare, it just runs off. So this is the big problem when ground becomes denuded and all the organic material is taken away from it. You get the opposite to the upward spiral that I described earlier on, right? With the upward spiral, you have a forest. The sun hits it, the sun beats down on it, millions of plants capture that energy gets deposited and used by a bunch of different things that live and die, and that builds soil, and that creates room for more plants, and more plants harvest more energy. That's an upward spiral, right? And so the overall stored energy is going up and up and up, and therefore the amount of life that the system can support goes up and up and up, right? But the opposite of that is a disturbed, damaged ecosystem, i.e. a desert, basically. And those are on the rise dramatically, right? It's going to become a huge problem, desertification, if we're not careful. And they're in a downward spiral because when it rains, the rain just, the tiny amount of fertile soil that there might be, the rain just carries it off with it. It's called erosion, right? And the sun hits it, but there's nothing to capture the sun, so it just bounces back off it. Now, what will nature do about this? What will nature's first defense likely be if you leave one of these things on its own?
Pioneer plant.
Yes. Yeah, pioneer plants. Pioneer plants are like tough, usually ground cover, usually adversity resisting, you know, like have the ability to resist or to deal with a lot of adversity, right? Because it's like, imagine trying to grow in a desert, that would be tough. And so you get pioneer plants, right? And so what we get is this type of graph here where this is the start of the disturbance. And this is, on this line we have diversity, and on this line we have stability. So after a disturbance, you have none of either. You have no diversity and no stability, right? And as you get, what you get in early succession is you start to get a rise in diversity. You start to get these early succession pioneer plants that can come in and that can like hold some of the sunlight and the water, and they come along and they do their thing, right? And they're usually grasses and ground covers, and then after a while, you know, they make their way into sort of like what we call like softwood trees and shrubs and things, right? And so the diversity starts to increase, and so does the stability. And most people can actually, once you point this out, most people can kind of recognize the difference between a primary growth forest and a regrowth forest. Regrowth forests tend to have a lot of like still softwood trees in them, and they tend to be very diverse because you reach a point somewhere along here in the mid-succession, where you kind of get like maximum diversity actually, because there's an awful lot of sunlight can get in, but there's also now everything is covered and there's an awful lot of life in there basically. And then little by little, we get into kind of peak or late succession, where our peak species come out. And that the peak species just depends on kind of what climate you're in. If you're in the tropics, the peak species will be things like, you know, Chico Zapote from Petén would be like a peak species, ultra hardwood tree that will kind of appear somewhere in the successional thing after about 50 years. You'll start to get Chico Zapotes growing, or, you know, mahogany trees. And the hardness of the wood is kind of a good indication to the amount of energy that's stored in the system, because hardwoods really they're just complex arrangements of carbon and minerals, right? And it's an interesting thing. Basically what happens, remember I was talking about the relationship between living and non-living species, living and non-living factors, right? So the living things are all, the plants, the decomposers, all of these things. The non-living things, one of the really important things in non-living things are the minerals, the pieces of rock. Because the pieces of rock, the tiny pieces of rock, the minerals, they're non-living and therefore kind of unavailable to everything in the biosphere, everything in the living sphere. But like the decomposers, the microorganisms, make them available. So because that's one of the things that that microorganisms and fungi do, is they actually they digest minerals and then they make them available to plants, and then the plants can take them up and incorporate them into their structure. And the more life you've got going on here, the more of the physiosphere that becomes available to the biosphere. So the more mixing you get, and so eventually you get these really incredible, like, peak species tree coming out. You know, in temperate climates it might be oak trees, here down here it might be mahogany trees, and these things are they're like the majestic trees, and they have really hard structures because they grow slowly and they incorporate all of the available things in the ecosystem get incorporated and embodied in the structure. But interestingly, species-wise, you start to get actually a tapering off, right? You start to get this tapering off because eventually the big peak species dominate the space, right? And they kind of cut off the available sunlight to things down below them. So that's interesting as well, because it also implies that death and destruction and disturbance is necessary, right? Because if you don't get a resetting of it, eventually it'll just kind of stagnate. Now, in fairness, diversity in old growth forests, plant species-wise, starts to go down, but life-wise, it starts to go up. You know, so the more, and what keeps going up. Oh, sorry, I drew this wrong. That's stability and that's diversity. Sorry. What keeps increasing over time is the stability, right? Stability is like the amount of time it can endure, because the more these big trees get their roots down and the more energy that's captured, the longer the things can last, and the more of a sort of a homeostasis occurs, and the diversity of plant species, like I say, goes down, but the overall energy capture goes up, and therefore so does the diversity in other species, especially animals, right? And so that's the way succession works. And just like with a lot of things I'm going to describe in the water lecture, in the soil lecture, we want to understand how this works in nature, and then we want to take the next step, which is to intervene and to use that knowledge to our benefit, right? You know, because a lot of the time in science, a lot of these processes get described as these kind of passive things that just happen, and there's no emphasis on the fact that, well, humans can actually intervene, and we can either cause ecological degradation or we can cause ecological regeneration. And so what happens in succession is that, yeah, this thing happens, and over like 40, 50, 60, 70 years, you get stable life-supporting forests growing on previously disturbed, unhealthy ecosystems. But human beings, if they're smart, they can accelerate this process into like 5 or 10 years, right? And that should be like very good news. And it's an area of permaculture called using successional models, right? And using successional models just means you take a big area of land and you plant lots of the early succession species, the things that produce biomass, the things that fix nitrogen, and the things that create the conditions for more life to occur, right? So you produce, so like, you know, an example of this would be kind of like, yeah, comfrey. We plant a lot of pigeon pea here. Pigeon pea is a nitrogen fixing, fast growing legume that produces food. Certain trees are amazing, like this one. This is Inga. It's a soft-ish wood. It's actually very good firewood, but it's incredible forage, and they grow really quickly, and they produce shit tons of leaves. Yeah, and they stay green. Up in Kenzie's land, where we're going to go, I think today, We planted like 1,000 of these last year, you know, and a lot of them will just be coppice species, right? As in things that will just get like chopped back continually and fall onto the floor. So we plant a lot of like nitrogen fixing. These are nitrogen fixers as well, right? They take nitrogen from the air and they put it into the ground. We'll cover nitrogen fixing species more in the plants lecture, but so we can use these successional models to speed up the rate of sort of ecological recovery, right? And then we can take advantage of this thing, right? Which is a lot of permaculture, a lot of like food forest systems and agroforestry systems. If we go back to this thing here where we have stability and diversity here, and you have a curve that goes like this. A lot of the time we want to work with this point here. So we want to kind of get our forest garden or our agroforestry system to the point of like maximum diversity and then keep it there. How do we keep it there? We try and get it there as fast as possible, right? Through using successional models, through planting our comfreys, our clumping grasses, our nitrogen fixers. So we want to get it there as fast as possible. And then we want to keep it there by pruning. Yeah, and pruning just means like lopping off branches and returning that organic material to the soil. Right? There's a really good, we might get to watch it, or else I'll put it in the lecture, in the suggested watching for after the course. Project Syntropy in Brazil. It's a really brilliant project. The guy's name is Ernest Gaucher, and he's just obsessed with pruning. He just plants these like agroforestry systems, which are just like productive forest tree species, but they plant lots and lots of things like this, nitrogen fixing, biomass producing trees, and they're just continually pruning and dropping the stuff down onto the floor. And then so in doing that, they're building up like a deeper and deeper layer of soil, you know. And so in doing that, they're speeding up ecological succession by like, you know, a magnitude of 10 at least. And so this stuff, I think, hopefully the idea with this stuff is it should be very like empowering and encouraging, because I think like Bill Mollison said that he's like the problems of the world seem endlessly complex, but the solutions are embarrassingly simple, and they really are once you start to understand this kind of stuff. So yeah, I think that's it. Like, so what did we talk about? What is an ecosystem? What do ecosystems do? They support an awful lot of life, and they create the conditions for more life to occur. How do they do it? They do it by capturing a large amount of energy and having a large amount of beneficial interactions. Yeah? And how do they get to that point? They get to that point through a process of succession, which if we understand, we can greatly speed up. Those are like the takeaway points from the lecture.